Howdy, howdy, this is Mr. Potter. Welcome to day 2 of our talks about implicit differentiation. Today what we're going to do is take a look at higher order derivatives using implicit differentiation. So one of the things that we need to recall is that whenever I'm trying to find y double prime, remember that that's really the derivative of y prime. So when we're taking these derivatives, we need to find y prime. We need to find dy dx. And the second thing that we're going to have to do is we're going to have to take the derivative a second time. So that's going to be our process here. First thing I'm going to do is take the first derivative a first time to find y prime. And the second thing I'm going to have to do is take the derivative a second time and substitute for y prime. In other words, every time I see y prime, I'm going to need to substitute that expression that's equal to y prime. And so that's what we're going to be doing in these problems. The algebra tends to get a bit messy when we start looking at a second derivative. But one of the things that we find in these second derivatives is that we can write them in a much more concise form once we actually go through the pains of the algebra involved. So I want to take a look at 3 examples today. And so here's our first example. I want to find y double prime if 2x cubed minus 3y squared equals 8. And so my first step, of course, is to find dy dx. So to do that, I'm going to take the derivative of each of these terms. So the first term is going to give me 6x squared. My second term, because I'm taking the derivative of something with y, I end up with 6y dy dx. And this is equal to 0, because the derivative of a constant is 0. And then we're going to go ahead and solve for dy dx here. So I'm going to move the 6x over to the other side. So I've got 6x squared over on the other side. And then I'm going to divide both sides by negative 6y. So I've got dy dx is equal to negative 6x squared over negative 6y. Or really just x squared over y. And this is important because in step 2, to find the second derivative, I'm going to take the derivative of this expression. So y double prime is going to be equal to the derivative of x squared over y. And in order to take this derivative, I have to use the quotient rule. And that's something that we're going to see a lot of, because a lot of times solving for dy dx using implicit differentiation gives us a ratio of 2 functions. I'm going to have to be using the quotient rule when I finally take this derivative of this fraction. So what I'm going to get over here is the denominator times the derivative of the numerator minus my numerator times the derivative of my denominator over my denominator squared. So with this expression, I've got y times 2x minus x squared times the derivative of y is dy dx. And this is all going to be divided by y squared. And the other thing that I'm going to notice is because dy dx is equal to a fraction, I'm going to have a fraction within a fraction. And so it's often going to be easier to write this as 1 over y squared, which is my denominator here, times this expression. So I'm going to have 2xy minus x squared times dy dx, which is x squared over y. And because I'm subtracting, I'm going to want to get a common denominator here. So I've got 1 over y squared times the expression. This is going to be 2xy squared over y minus x to the 4th over y. And because I have a common denominator, I could really write this as 2xy squared minus x to the 4th over y. But because I'm multiplying by this 1 over y squared, this ends up being over y cubed. And so this is what my second derivative is equal to. 2 times x times y squared minus x to the 4th, all divided by y cubed. And so as I said, the algebra is a bit involved. But we're going to see an interesting trick that we can use on these next 2 examples. The key thing to remember, though, is that it's a 2-step process. The first thing I'm going to have to do is to find dy dx. And once I've solved for dy dx, I'm going to take the derivative a second time to find my second derivative, y double prime. And it's going to involve quotient rule because I'm always going to end up with this relationship over here that's a ratio. And so rewriting the denominator as 1 over the denominator, and that allows me to get a simpler form here. So our next example, I want to find y double prime if x to the 2/3 power plus y to the 2/3 power equals 1. So my first step is to take the derivative of each of these terms. So this is going to give me 2/3 x to the negative 1/3 plus 2/3 y to the negative 1/3 dy dx equals 0. And again, anytime I take the derivative of a term that involves y, I'm going to be getting a dy dx term that pops out. So I need to solve for dy dx. I'm going to move this 2/3 term over to the other side. So I'm going to have 2/3 y to the negative 1/3 dy dx equals negative 2/3 x to the negative 1/3. And then I'm going to want to divide by this coefficient to get dy dx by itself. So I'm going to divide by 2/3 y to the negative 1/3. So I have negative 2/3 x to the negative 1/3 in my numerator, and 2/3 y to the negative 1/3 in my denominator. And I see that I've got a common factor here. But the other thing I notice is that because both of these have negative exponents, both of these would end up being flipped. So I end up with negative y to the 1/3 power over x to the 1/3 power. So this is y prime. So now my second step would be to take the derivative of that. So if I want to find y double prime, I've got to take the derivative of this negative y to the 1/3 divided by x to the 1/3. And I'm going to have to use the quotient rule. So I'm going to have my denominator times the derivative of my numerator. So this is going to be negative 1/3 y to the negative 2/3 dy dx minus my numerator, which is negative y to the 1/3, times the derivative of the denominator, which would be 1/3 x to the negative 2/3, all divided by my denominator squared, which would be x to the 2/3. And as I did before, I'm going to write that denominator in front because I want to deal with the rest of this algebraically. So I'm going to have x to the 1/3 times negative 1 over 3 times y to the 2/3, because that 2/3 makes the y go in the denominator, dy dx. But dy dx is this fraction here, negative y to the 1/3 over x to the 1/3. And some magic is going to happen there. Minus, here I've got negative y to the 1/3 times 1 over 3x to the 2/3. And so I see a couple of things that I can do here. Number one, I do have a common factor here and here, so I can divide that out. Number two, I do have a common factor in the numerator and denominator here in the case of the y to the 1/3 power, so I could really think of this as just being y to the 1/3 power. Third, I have a minus and a negative, so that really becomes an addition problem. And fourth, because of the 1/3 here and the 1/3 here, I really could factor out a 1/3. So I could really make this 3x to the 2/3. And with what I've got left, of course, my negatives cancel out. So I'm left with just 1 over y to the 1/3 power plus y to the 1/3 power over x to the 2/3 power. So I've been able to do a lot of algebraic simplification here. And when I got a common denominator, I'm going to be able to do even more. My common denominator would be y to the 1/3 times x to the 2/3. This is missing the x to the 2/3. And this is missing the y to the 1/3. So I'm going to have 1 over 3x to the 2/3 times, and over here with this common denominator of x to the 2/3, y to the 1/3, I'm going to have x to the 2/3 plus y to the 1/3 plus 1/3 makes 2/3. And so I've got this nice closed formula, but I do have one more trick up my sleeve. In my original problem, I knew that x to the 2/3 plus y to the 2/3 equals 1. And so that means this numerator is really 1. So I have 1 over 3x to the 2/3 times 1 over x to the 2/3 times y to the 1/3. And so I can write this in a much nicer, more concise form. 3x to the 4/3 y to the 1/3. And considering how convoluted the algebra got in the process of solving for the second derivative, this is really a fairly nice example of a second derivative. I certainly would much rather substitute here one value of x and one value of y than substituting up here for all these individual values of x and y. So again, the idea here is I'm going to have to find y prime first, get it in a nice form so that I can then take the derivative and substitute when I need it. Notice that this dy dx here became the y to the 1/3 over the x to the 1/3 that I used in the algebra problem. So we have one more example we're going to go through. What I've got here is find y double prime if x squared minus xy plus y squared equals 1. And so again, the two-step process, the first thing I'm going to do is take the derivative of each term. So I'm going to have 2x minus, now I'm going to have to take the derivative of a product here, plus 2y prime equals 0. And then here, when I'm taking the derivative of this product, I'm going to have first times derivative of the second plus second times derivative of the first plus 2y prime equals 0. And again, I'm using y prime because it's a much shorter way of writing dy dx, but it really is the same thing. I still want to get my y prime terms by themselves, so I'm going to need to move these other terms to the other side. So I'm going to have y prime times 2y minus x, that 2y minus x. And that's going to be equal to, when I move the y over and when I move the 2x over, I get y minus 2x. And so my first derivative is y minus 2x over 2y minus x. And so this is the first step, finding y prime. So on the second step, I'm going to need to take the derivative of that. And again, I'm going to have to use the quotient rule. So I'm going to have the denominator, 2y minus x, times the derivative of the numerator, which is going to be dy dx, minus 2, minus my numerator, y minus 2x, times the derivative of my denominator, which would be 2 dy dx, minus 1. And this is all over my denominator squared, 2y minus x squared. And as we did before, I'm going to write this as 1 over 2y minus x squared, so I can deal with the fraction within a fraction that occurs when I have this dy dx term. So I'm going to have 2y minus x times y minus 2x over 2y minus x minus 2 minus y minus 2x times 2 times this fraction, y minus 2x over 2y minus x minus 1. And as I did before, I'm going to want to get a common denominator within this larger parentheses term. So I still have this 1 over 2y minus x quantity squared. But over here, I'm going to have 2y minus x times y minus 2x minus 2 times 2y minus x over 2y minus x. Minus, over here I've got y minus 2x times 2 times y minus 2x minus 2y minus x, all divided by 2y minus x. And I notice that because I have this common denominator term, I really can factor that out, and so this outside denominator becomes 2y minus x quantity cubed. And at this point, I've got 2y minus x times, over here when I distribute this negative 4y minus 2x, that's really a plus 2x, and this term will cancel out, leaving me with just a negative 3y. And over here when I subtract, I've got y minus 2x times, when I distribute here, I'll have 2y minus 4x minus 2y plus x. I'll end up with negative 3x. And so, yeah, there's a lot of algebra going on here, but it really is going to simplify quite nicely. So when I distribute, I'm going to have 2y times negative 3y, which is negative 6y squared. I have negative x times negative 3y, which would be positive 3xy. I'm going to have negative y times negative 3x, which is going to be a positive 3xy. And then I'm going to have negative times negative times negative, which is going to be negative 6x squared, over this denominator of 2y minus x cubed. And of course, I see that this 3xy and this 3xy is really going to be a positive 6xy. And I see that I can factor a negative 6 out. So when I factor a negative 6 out, I end up with a positive x squared, that's this term, minus xy, plus y squared, that's this term, all over 2y minus x cubed. But again, as I mentioned, whenever I see x squared minus xy plus y squared, I can substitute a 1 for it. And so this ends up really being negative 6 times 1 over 2y minus x cubed. A much more concise form, something that's very easy to substitute, and something that I didn't believe I would ever reach having gone through all of this algebra. But this is one of the things that we notice about our functions, especially if our functions show some level of symmetry, as they did here, or as they did in our second example. Seeing this symmetry in here leads me to believe that I'm going to have some type of symmetry in my second order derivatives. And so it's really something nice to see, something nice to look at algebraically, because ultimately we're going to be wanting to know the values of these first and second derivatives at particular points. And having a simple closed form, something where I'm going to have to substitute into x at one place or substitute into y at one place, is going to make it much more convenient for myself. So that's higher order derivatives using implicit differentiation. I'm Mr. Potter. Thank you for watching. Have a great day.